Chemical bonding is a very simple topic, but because it's so simple, many students just take it lightly. They say, oh, just a couple of terms, no big deal. And then later on, they come to regret it. I'm explaining something and I say, well, the reason for this is because maybe this is an ionic compound. And the student will look at me and say, so what? What does that have to do with anything? Well, go back to the chapter on chemical bonding and then you'll understand. So you might as well get it right from the beginning. It will save you aggravation, time, headaches. Chemical bonding is going to be responsible for the properties of matter. Remember when we talked about the atom, I said, isn't it amazing that the chair that's made up of atoms that are mostly empty can hold your weight? Isn't it amazing you can walk through a wall? And at the time I said, the reason for solids to be solids, for the chair to be able to hold you, is the chemical bonds. So that's what we're going to be talking about today. Okay. Besides, chemistry is all about bonds. Go back to Dalton. Dalton said in a chemical reaction, atoms get rearranged. They don't change, they just get rearranged. Well, how do you rearrange atoms? Well, you have to break the old bonds that was holding the atoms together, and when you put them in a different order, you have to form new bonds. So it's obvious you need to understand what bonds are. Now, atoms don't change in ordinary chemical reactions. And by ordinary, I mean non-nuclear chemical reactions. Okay? That means the identity of your atom does not change. If I have, for instance, hydrochloric acid reacting with sodium hydroxide from sodium chloride and water, none of these atoms change. The hydrogen remains hydrogen, the chlorine remains chlorine, the sodium remains sodium, the oxygen remains oxygen. That means the atomic number did not change, the nucleus of the atom did not change. So what changes? The electrons. And not all electrons, okay? We are really talking here about valence electrons. These are the ones that participate in chemical reactions, and they can be gained, they can be lost, they can be shared, and some students get the idea that this is a random process, almost kind of like the atom draws a card that says gain 3 electrons. I don't like it. Let me try again. And they draw another card, lose 1 electron. Yeah, that sounds good to me. No, that's not the case. Okay? There's a very important principle in here. Atoms will do whatever they need to do to achieve a full outer shell because that makes them very stable. Now we call this the octet rule because for most of the atoms you're going to be dealing with, the outermost shell contains 8 electrons. There are exceptions. You have very small atoms like hydrogen. Hydrogen is filling the 1s orbital, so all it can hold is 2 electrons. And then you're going to have really big atoms that can hold more than 8. But for the purposes of this course, we are going to say the outer shell is filled with 8 electrons. So sometimes electrons, like I said, they're transferred, they're lost or gained. I use the word transfer because you cannot lose them to the atmosphere. You cannot find them in your kitchen drawer. A lost electron has to go somewhere to another atom. And an atom that wants an electron has to get it from somebody else. So actually you're transferring electrons from one atom to another. When you're transferring electrons, you're going to form ions, and we'll go into a little bit more of detail in a moment. And the electrostatic attraction between those ions forms an ionic bond. Sometimes electrons are going to be shared instead. This time you form molecules, and notice that I did not say molecules with the ionic bonds. Just wait, we'll cover all of that, I promise. But this time you form a covalent bond. So compounds are going to be classified as ionic or molecular, some people call them covalent, based on whether you have ionic bonds or covalent bonds. The properties of ionic and covalent compounds are very, very different, and they're based, like I say, on the bonds. So we need to understand the bonds. So we begin with ionic bonds. We said that when electrons are transferred, we form ions. Why? Because you have one atom losing electrons. Let me bring you back to the original theory of the atom. And remember, we say in the neutral atom, the number of protons that are positive charges equals the number of electrons that are negative charges. What happens if you lose electrons? Now you have more positive charges than negative charges, so you form a positive ion, and we call that a cation. The ion that gains electrons now has more negative charges than positive, so you get a negative ion that we call an anion. Both are formed because the electron moves from one ion to the other, so you have a positive and a negative ions, and again electrostatic attraction between the two of them form the ionic bond. One thing I remember when I first took chemistry was, how do I remember who is the anion, who is the cation? Because I hate memorizing. Well, a couple of years ago, one of my chemistry students wrote in an exam the following, and I like to share it. Cats are positively, and I like the way he spelled it, since he's talking about cats, positively great. Now, maybe he had a cat that he loved. That was at a college near Clemson, so maybe he was talking about Clemson Tigers. I don't know. It doesn't matter. Cats positively. That's an easy way to remember who's a cation, isn't it? So whenever I develop a trick or I learn something from my students, I'd be glad to share with you. Okay? So the typical example of an ionic compound is sodium chloride. You look at the periodic table, sodium has 11 electrons. So we have 2 electrons in the first shell, 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8, that's 10. In the third shell, it has only 1 electron. Chlorine, and I never leave enough room, has 17 electrons, so 2, 1, 2, 3, 4, 5, 6, 7, 8, and in the outermost shell, it's going to have 7. 5, 6, 7. Neither one has a full outer shell. So let's look at sodium. In theory, sodium could gain 7 electrons, and that would fill the third shell. Or it can lose 1 electron because the shell immediately before is already full. Remember the Oxford principle? We have to fill the shells in order. So the next to the last shell is already full. Now, if you have to do something and they give you a choice between doing it once or doing it 7 times, most people will choose once, right? Sodium is no different. He'd rather lose 1 electron, it's easier. So what we have in there, sodium, that now has only 2 full shells, 7, 8. The outermost shell is full, sodium is happy, but it has lost an electron, so what you have here is a sodium ion, positive charged. Chlorine has a similar situation. It can gain 1 electron, and the third shell will be full. It can lose 7 electrons. Once again, 1 versus 7, he'd rather gain the 1. So you have chlorine with 2, 1, 2, 3, 4, 5, 6, 7, 8. And now the third one has 8. 1, 2, 4, 5, 6, 7, 8. The outermost shell is full, chlorine is happy, but it gained an electron, so you have a negative charge in there. So you see in here how first you have to have 2 atoms, one that loses electrons, one that gains electrons. You form 2 ions of opposite charges, they're going to attract each other, and you form an ionic compound, sodium chloride, table salt. Okay? So when we talk about ionic compounds, we're usually talking about a metal and a non-metal, because metals are very likely to lose electrons, and non-metals prefer to gain electrons. Look in the periodic table, metals are located on the left side, so they have very few valence electrons, they rather lose them. Non-metals are on the right side, they have 5, 6, 7 valence electrons, so it's easy for them to gain electrons. So whenever a metal and a non-metal react, usually you form ionic compounds. This is something that you want to remember. Let me just call non-metal reacting with a metal. Because in the next video, we are going to be talking about nomenclature. and the rules are different for ionic and covalent compounds. So the first question I'm going to ask you when I give you a particular molecule is this ionic or covalent? Because once you determine that, then you know what set of rules to follow. So remember, ionic compounds is a non-metal and a metal. Okay. The essence about ionic compounds is that they don't form molecules, they form crystals. Basically, you have attraction between ions, but this particular chlorine in here, for instance, is not only attracted to one sodium, it's attracted to the sodium that is in front of him, to the sodium behind, to the one on top, the one at the bottom, the one on the right, and actually there should be one on the left too. So every ion is attracted to all of the ions of opposite sign that surround it. In this particular case, you can tell 1, 2, 3, 4, 5, 6. There are many different crystalline structures and the number of ions varies. But this is very important. First, you don't have a sodium chloride molecule. You have a crystal that has many sodiums and many chlorines. And when I write the formula sodium chloride, what I'm really giving you is the ratio of sodium to chlorine. But you don't have an individual sodium chloride. The other thing is that you can tell that every ion is surrounded and attracted to many other ions. So not only there are strong forces, but there's lots of them. So that makes the solids very difficult to separate the ions. If you add heat, you're going to have to break a bunch of different bonds. So they tend to be solids with very high melting points and very high boiling points, because you have to break so many ionic bonds. Because in the solid state, the ions are fixed in place by the other ions, they are poor conductors of electricity. But it is all very ready in water, because we are going to see that water is a polar molecule, so water can get between the ions, and when it gets between the ions, we'll talk more about that in the future, but basically it disrupts the ionic bond, so the ions separate. So most ionic dissolve very easily in water. Now, once you dissolve them, we said the ions are separated. There's no attraction between them. Same thing when you melt them. So now that the ions are free, the dissolved or melted ionic compounds become very good conductors because the ions can move freely. Okay? Can you predict the charges of your ions? Most of the cases, yes. You can just use your periodic table. Look at the main group metals. Group number 1 has one valence electron. So group number 1 loses the valence electron and forms a +1 cation. Group number 2 has two valence electrons. So group number 2 is going to lose those two and form a +2 cation. We are going to skip for the time being transition metals. We'll get back to them. Group 13 has 3 valence electrons. So it loses the 3 valence electrons and forms ions with 3 positive charges. Look at the non-metals now. They have lots of valence electrons. They're almost there. So they're going to be gaining. Group 17, they have 7 valence electrons. So they want to gain one and form a -1 anion. Group 16 has 6 valence electrons. So they're going to gain 2 electrons and form a -2 anion. Group 15 has 5 valence electrons, so they want to gain 3 and form a -3. So right there, you can see that a bit over half of the ions, you can predict them just by looking at the periodic table. And you should always have a periodic table with you, okay? I always put a periodic table in my exams, but I tell the students, print it out and bring it to the exam. That's your best friend. You're going to be using it all the time. Now, this is an example, calcium. When you look in the periodic table, calcium is in group 2. So right there, you know it's going to form a +2. You can also look it up and say, oh, the atomic number is 20. That means I have 20 protons, 20 electrons. If you look at the electroconfiguration is going to be argon for S2. So it has 2 valence electrons, which we suspected because it was in group 2. So it's going to lose 2 electrons. If you have 20 protons, 18 electrons, obviously it's going to form calcium plus 2, which we had predicted in there. So it's very easy to make predictions like this. Now, the problem comes with the transition metals and a few of the main group metals. Basically, we're talking about metals in which you have d orbitals. And we are going to blame many of our problems to d orbitals. I usually refer to transition metals as 2-year-olds. Okay? They know what they're supposed to do, and they do what they want to do. So when transition metals lose electrons, they don't necessarily lose them from the s orbital. They may lose them from the s, they may lose them from the d, they may lose one from each. So that's why they can make more than one ion. Okay? Look, for instance, iron. Iron can lose 2 or 3 electrons. So you get iron plus 2 and iron plus 3. That means we have to add something to the name. Whenever I have only one student with a particular first name in class, I can just call that student by name, no problem. But if I have more than one, I have to use the last name, right? Because one semester, I couldn't believe it. I had 7 girls named Ashley. That was unusual. But this is common to have 2 students with the same first name, so you have to call them by first and last name. How do we give the ion a last name? We use the charge of the ion, we write as a Roman numeral in parentheses, and we put it behind the name of the metal. So iron plus 2 is iron 2. Iron plus 3 is iron 3. Now, be careful. Warning. I have plenty of students who don't realize this is only for the ions that can form more than one, for the metals that can form more than one ion. So I had students writing an exam, something like if asking to name the atoms in a particular molecule, and they write like magnesium 2. And I said, wrong. And they get very upset. What do you mean? The ion was magnesium 2 plus, so it's magnesium 2. No, because the rule says you put the last name, you put the Roman numerals only when that particular metal can form more than one ion. If you can form only one ion, there's no need. You don't do it, period. They get so upset. Well, listen, this is not my rule. This is not the textbook's rule. It comes from the UPAC, the International Union for Pure and Applied Chemistry. And all chemists all over the world follow UPAC rules. End of the story. Okay? So be very, very careful. This is a common mistake. So we have here a list of ion charges. And you say, how am I going to memorize all of them? Well, don't worry. Because group 1, you can predict it. Group 2, you can predict it. Group 13, you can predict it. 15, 16, 17, we know noble gases don't form. So what you have left is a handful in here that, yes, there's no way around it. You just have to memorize these ones. Okay? I'm always going to try to limit memory in chemistry as much as possible, but sometimes you just have to memorize things, and this is one of those. We also have polyatomic ions. Up until now, all of the ions we had looked at were monatomic, meaning there was just one atom that had become an ion. But sometimes you have a molecule that has gained or lost electrons, is electrically charged, so we call that a polyatomic, meaning several atoms, ions. And they behave as one. We're going to see polyatomic ions don't usually break, they react as a group. A particular type of polyatomic ions that's very common in chemistry is oxyanions. An ion tells you it's a negative ion, it's a polyatomic ion, and it has a lot of oxygen. Okay? So we are going to be looking at some of these ones. How do we name oxyanions? Well, the rule says that if you can form 2 oxyanions, let me give you an example. You have SO4, 2 minus, and SO3, 2 minus. The one that has the larger number of oxygen atoms is going to use the ending 8. So this is sulfate. The one that has the smaller number of oxygen atoms is going to have 8. So this is sulfite. I know you say, well, this helps you if they give you both of them, but if they ask you write down sulfate, I'm afraid you're going to have to memorize it. But this is an explanation of why it gets that name, and sometimes you're going to have both of them, and you will be able to identify. Sometimes you can form more than two. Halogens are infamous for that. So halogens can form ClO, ClO2 minus, ClO3 minus, ClO4 minus. So how do we name them? We took the ones in the center and we follow the rules that we just discussed. So the one that has most out of those two, the one that has more is going to end in 8. So we call this chlorate. The one that has less, we're going to have the ending 8, so that's chloride. Now, if you have even more oxygens than the largest one, then you put the prefix per. So this one that has more, this is 3, this is 4, so this one has more, is more than chlorate. That's what per means. So we call it perchlorate. And if you have one that has even less than the one with the least, we put the prefix hypo, that means below. So the one that has less oxygen than chloride is going to be called hypochlorite. Okay? So these are the rules. Like I said, you're still going to have to memorize. Here you have a number of polyatomic ions. The sooner you memorize them, the better off you'll be. Okay? We're going to be using them all the time. I don't know your instructor, but I always tell my students, we're going to be using them from now on. I'm going to be using the names, and I'm going to assume that you know what it is. Okay? I want to mention one unusual thing here, bicarbonate. That doesn't follow any of the rules. What does that bi mean? Well, the reason we still use bicarbonate is because this is an old traditional name, and sometimes not even the UPAC can stop chemists from doing things the way we've always done it. Okay? So bicarbonate is actually hydrogen carbonate. So carbonate is CO3, 2 minus. If you add the proton, it becomes HCO3, only one negative charge. That's hydrogen carbonate or bicarbonate. If it was up to the UPAC, everybody would use hydrogen carbonate, but like I said, people have been calling baking soda bicarbonate for centuries, and sometimes not even the UPAC can make people stop. So finally the UPAC says, okay, we'll make an exception with bicarbonate. You can use it. We don't like it, but it's easy to tell them you can use it when you cannot enforce it. The question would be, why did they decide to call it hydrogen carbonate? Well, in this case, you can say it would be easy to memorize that one, but let's see, for instance, phosphate, PO4, 3 minus. You could add one proton, and you have HPO4, 2 minus. You could add 2, HPO4. So what if you call both of them biphosphate? By doing the same thing that we do with the carbonate, we call them bicarbonate. If you call them biphosphate, you don't know which one. But if you call them, and remember the first one we just said that's phosphate. If you call the first one hydrogen phosphate, and the second dihydrogen phosphate, then you have a different name for each one, and these names are very descriptive. They tell you it's a phosphate with one hydrogen, it's a phosphate with 2 hydrogens. So yes, the UPAC name is better, but like I say, everybody agrees to make an exception for bicarbonate. But this list Take your time, but try to get them memorized at your earliest convenience. So we move to covalent bonds. Okay? We said that a covalent bond is formed when two atoms share electrons. And you wonder why they share electrons. Usually it's because they have similar tendencies to attract electrons. Let me give you an example. Let's think of carbon. Carbon has 6 electrons, so 2, 4. 2. So by the same reasoning we did before with the ionic, you say carbon could gain 4 electrons, and then fills that cell. It could lose 4 electrons, and then the lower cell is full. Which one does he choose? Well, when it was 7 versus 1, it was easy. But when you have 4 versus 4, carbon says, I don't care. It doesn't matter. It doesn't have any strong tendency to do either one. We have a problem there. Let me give you another example. Nitrogen and oxygen. Nitrogen has 5 electrons in the outermost shell. 3, 4, 5. Oxygen, 1, 2, has 6. 2, 3, 4, 5, 6. So imagine nitrogen walking up to oxygen and says, hey, give me 3 electrons. And oxygen says, you crazy or what? I need 2 electrons. But I ask first. It doesn't matter. I'm not giving you 2 electrons. They can argue until the end of time. Until the final say, I'll tell you what. Why don't we just share the electrons? No, but that's the problem. We're talking about non-metals. Nobody wants to give electrons. Everybody wants to gain electrons. So eventually they agree, let's just share electrons. Let's see how that works. The easiest example is hydrogen. You have a hydrogen that has 1 electron, another hydrogen with 1 electron. Once again, no one wants to give up the electron to the other one. Okay, we are going to share. Let's put it like this. And the electrons now belong to both of them. Every electron is going to go around the hydrogen in the left, then the hydrogen in the right. Basically, it's like it goes around like that. And the same thing with the other electron. So both electrons belong to both hydrogens. That's what holds them together. That's the covalent bond. And it works. Even though you said for 2 hydrogens to fill the outermost shell, you need 4 electrons. No, by sharing, both electrons belong to both of them. And the fact is, hydrogen gas is very stable. It's not going to break apart into hydrogen atoms. It works. Now, when the 2 atoms are identical, like we did with hydrogen, it's no big deal. They both attract the electrons with the same strength. They're shared equally. You can say each electron spends 50% of the time over one hydrogen, 50% of the time over the other hydrogen. So we call that a pure covalent bond. Now, if you've ever tried to share an assignment with somebody else, you know that hardly ever works, right? There's always one person who works more. Well, when the atoms are different, they're going to have different attraction for the electrons. Okay? So one is going to attract more than the other one, and that's going to shift the electron density towards the strongest atom. It's like playing a tug of war. If the 2 people are identical in size and strength or very, very similar, it's going to go on for a while. But if you have a really big boy and a teeny girl on the other end, it's over before you know it, right? So when the distribution of electrons is not 50-50, but it may be 60-40 or maybe 70-30, we call that a polar covalent bond because the charges are polarized. The strongest atom is going to have the electron more than its fair share and develops a partial negative charge. This is the case of hydrogen chloride. The weakest atom is going to have the electrons less than we're supposed to have it, so it develops a partial positive charge. These are very, very, very small charges, okay? They're not even a charge, and then one electrical charge is very little, so a fraction of that is tiny. But this is going to become unbelievably important in chemistry, okay? And we'll talk about that in the future. So molecular compounds, the ones that are covalent compounds, use covalent bonds to solve from a covalent compound and produces molecules. We don't have crystals now because we don't have ions attracted to a bunch of different ions. We have isolated molecules. If you have a pair of tweezers small enough, you could pick up a molecule of water. You do have an isolated molecule of water. Like I said, molecular compounds are usually two nonmetals. We said ionic was a metal and a nonmetal. Now it's two nonmetals. Because you don't have a bunch of different attractions, but only the one attraction between the two atoms, they're usually either gases or low boiling liquids or low melting solids. So, like I said before, the type of bonding that you find is going to determine the properties of the matter. This is pretty much going over the same thing that we talk about, that pure polar covalent bonds. I don't think there's anything new in here. I use a vector here to represent the vector points towards the partial negative charge, but I've learned through the years that many students have a hard time dealing with vectors. We are going to try to avoid it as much as possible. You can understand chemistry without that. This is no different, just repeating the same stuff. So what is the force that the atom elects attracting the electrons? We call it electronegativity. Okay? So electronegativity is a measure of the tendency of an atom to attract electrons, or the electron density. So the more strongly the atom attracts the electrons, the larger the electronegativity, which means the most electronegative atom is going to pull the electrons towards himself, is going to have the most electronegative atom is going to be the one that has the partial negative charge. The least electronegative is going to have partial positive, and you say, well, that sounds good, but how do I know? There you go. The researcher in California studied the new fluorine was most electronegative. So they assigned randomly the value of 4.0. And I've heard all sorts of stories. I'm not going to chase the rabbit now. But basically what they did was compare the electronegativity of all their atoms to fluorine, and they were able to assign numbers. I want you to notice that since fluorine is the most electronegative, electronegativity increases from left to right and decreases from top to bottom. So if you have two atoms, you can say who is more electronegative than who by their position on the periodic table. Sometimes we're going to see that you actually need to know the number, but you don't need to memorize this table. It will be given to you. Okay? So electronegativity is going to determine the bond type. We said two atoms that are identical or maybe a very small difference, that's going to form a pure covalent. If the difference in electronegativities is zero or very, very, very little, okay? If it's small enough, we're going to include it in there. It's pure covalent. If it's somewhere so-so, there's a difference, but not tremendous. You have a polar covalent. But if the difference is very big, then the most electronegative atom actually steals the electron. It pulls so hard, it snatches it away. And you end up with an ionic bond. And you can say, well, that sounds real good, but how do I know? What do you mean by intermediate or large difference? What is very small? Fortunately, the UPAC set on numbers, okay? So if the difference in electronegativity is less than 0.4, we call it pure covalent. If it's between 0.4 and 1.8, we call polar covalent. If it's more than 1.8, it's ionic. And yes, you do need to know these numbers, although if you are honest, all you need to remember is 0.4 and 1.8. Makes sense. So let's go back in there and say, okay, what kind of bond will you form between nitrogen and oxygen? We talked about that before. And you say, well, oxygen is 3.5. Well, nitrogen and oxygen is 3.5, and it doesn't matter who you subtract from who. And nitrogen is 3.0, so the difference is 0.5. 0.5 is bigger than 0.4, right? So that is polar covalent. How about when we look at the example of hydrogen? Well, hydrogen is 2.1. The hydrogen is 2.1. The difference is 0. 0 is less than 0.4. So that's pure covalent. How about the example that we saw before of sodium chloride? And you say, okay, chlorine is 3.0, sodium is 0.9, so that's going to be 2.1. 2.1 is bigger than 1.8, so that's ionic. You see, when you look at the difference in electronegativities, we come up with the same results we had discussed before. And like I said, you don't need to worry about the actual numbers because they will be given to you. So if you'd like to work on one with me, I have worksheets where I give you examples and you determine what kind of bond, something like that. If you want to prepare for an exam, there's a link to my Wysand profile in the video description. Make an appointment and I will be more than happy to work with you.